Welcome to the deep dive. Ever wonder how a building actually handles an earthquake?
Yeah, it's not just sitting there passively, is it? There's a whole interaction going on.
Right. So today we're diving into how structures interact with, the ground itself. You sent over this detailed FEMA guide on something called soil structure interaction, SSI.
Exactly, SSI. Think of it as the hidden conversation, really, between the building and the earth when things start shaking. This FEMA guide, it's crucial for engineers.
Okay, a conversation. I like that. But why does this matter for you, our listener, if you're not an engineer? Why care about this soil stuff during a quake?
Well, it's easy to think of buildings as just like solid blocks,
Mm.
but they're dynamic and how they're connected to the ground. That drastically changes how they feel those earthquake forces.
Hmm.
Understanding SSI sort of pulls back the curtain on this hidden layer of complexity in keeping buildings safe. The ground isn't just a platform, it's an active participant.
Gotcha. So it's not just building on the ground, it's building with the ground's behavior in mind. And this FEMA guide, it's based on some pretty solid stuff, right? The codes and research.
Oh, absolutely. It digs into building codes like SSI 716 and 4117. Those are like the rule books for engineers. And it also pulls in research from NIST, the National Institute of Standards and Technology. So yeah, it's about taking all that complex research and making it usable, practical guidance.
Which is what we try to do here, right? Make the complex stuff understandable, maybe even a bit mind-bending. Because looking through it, some things really jumped out. Like, I honestly had no idea that just how wide a building is could change how it feels in an earthquake. Is that right?
It is, yeah. That's one
That,
of the fascinating parts.
or that sometimes letting the foundation move a little bit could actually be good. That seems weird.
It does sound counterintuitive, doesn't it?
Yeah.
But yeah, you've hit on some key points. Take that large footprint idea. A wide base can sometimes average out the really rapid,
Yeah.
jerky shaking. It's called base slab averaging.
Averaging? How? Because the shaking isn't hitting everywhere at once.
Exactly. The seismic wave arrives at different points under a large foundation at slightly different times. So the overall effect on the structure, especially from that high-frequency shaking, can be reduced.
Huh. Okay. And the flexible foundation thing.
Right, so sometimes allowing a bit of flexibility, maybe even some rocking at the base, can be a deliberate strategy.
Well,
It can help dissipate energy or shift forces in a way that actually protects the main structure above.
flexible being better sometimes. Wow. Okay. My interest is definitely piqued. So when does this SSI stuff really become a big deal? When do engineers absolutely have to focus on it?
Well, the guide highlights a few key scenarios. One, as we just mentioned, is buildings with a really large footprint. Big warehouses, stadiums, that sort of thing.
Where that averaging effect would be more pronounced.
Precisely. Another big one is when the foundation is embedded deep in the ground, like buildings with several basement levels.
Right. Like burying it deeper gives it more stability.
Kind of. That embedment provides more contact with the surrounding soil, which can dampen the motion and reduce the forces transmitted up into the building. It's like trying to shake something partially buried versus sitting on the surface.
Makes sense. What else?
Then you have situations with a big mismatch in stiffness. Imagine a really, really stiff, rigid building on top of quite soft, maybe squishy soil.
Okay.
That interaction can actually change the building's natural vibration characteristics.
Mm-hmm.
It often leads to a lengthening of the building's natural period, the time it takes to sway back and forth.
So it changes its natural wobble frequency.
Yeah. And depending on the earthquake's characteristics at that specific site, lengthening the period might be good, or it might actually make things worse by moving it closer to a frequency where the ground shaking is stronger.
So it's a tuning issue almost. You have to consider the building and the soil together.
Exactly. And the last major one is foundation rocking. We touched on this. If the soil has some give, the foundation might rock slightly.
Which still sounds a bit alarming.
It can be, but sometimes it's beneficial. Think of it as a sort of fuse. In a building with braced frames, those diagonal steel members,
Yeah.
a little bit of rocking at the base can prevent those braces from getting overloaded and buckling, which is a major failure point.
Yeah.
The movement happens at the foundation level instead of damaging the brace itself.
Okay, so it concentrates the movement, the deformation down at the soil interface?
Exactly. Same idea for shear walls, those big solid walls. Rocking can protect the wall by letting the movement happen at the foundation. It's about managing where the energy goes.
That's really interesting, allowing movement to prevent damage elsewhere. So, okay, an engineer starts a project. How do they get a quick sense if SSI is something they really need to dig into deeply? Is there like a first pass check?
Yes, Thankfully. The guide suggests a pretty straightforward rule of thumb test. It basically involves looking at two things: the soil stiffness, specifically the average effective shear wave velocity,
Okay, how fast seismic waves zip through the ground there.
right? And the building's own natural vibration period, assuming its base is completely fixed, like bolted to bedrock. We call that the fixed base fundamental period.
So you compare the soil's jiggle speed to the building's natural wobble time.
Kinda, yeah. That comparison gives a quick indication: is the interaction likely to be significant enough to warrant a detailed SSI analysis? Or is it probably negligible for this particular building and site? It helps focus the effort.
Smart. Okay, so let's say the rule of thumb says, yep, pay attention to SSI. What are the key effects engineers then model and design for? How do they actually do it?
Okay, so we've mentioned base lab averaging, that idea that shaking isn't uniform across a big footprint.
Right, the wave hitting the long dock analogy.
Exactly. Engineers quantify this using an effective foundation size, usually called B.
Yeah.
It's derived from the actual foundation area, and it helps calculate how much reduction you might get in those high-frequency forces.
Are there limits on when you can use this averaging? Like, does it work everywhere?
No, there are definitely limits. It's generally not used for very stiff soil sites like rock. And the current formulas are sort of calibrated for certain ranges of soil stiffness, though the guide mentions that stiffness limit might actually be removed in future code updates.
So the science is still evolving.
Constantly. And importantly, the main code, ASCE 716, currently only lets you apply this averaging effect if you're doing a very complex type of analysis called nonlinear response history analysis.
Not the simpler methods. Got it. What about the embedment effect? How deep the foundation is buried?
Right. So deeper embedment generally reduces forces. Engineers define an embedment depth, or a simple mat foundation is just the depth to the bottom. But for separate footings, it's a bit more complex.
Didn't you mention something about 75%?
Yes. The code says you can consider the embedment down to the bottom of the footings only if the foundation area at that deepest level covers at least 75% of the building's total footprint.
So if you have a partial basement, maybe covering only half the area, you might only get credit for embedment down to the basement slab level.
Exactly. The effective embedment depth used in the calculations would be shallower. The guide actually has some good pictures showing this.
And how do they translate that depth into reduced forces? Is there a factor?
Yep, there's a modification factor, usually called RRS. It depends on the embedment depth and the soil properties, and it directly reduces the spectral acceleration values used in the design.
Okay, so we've adjusted the input shaking.
Yeah.
Now, what about the flexibility? You said assuming a rigid base isn't always realistic.
Far from it, often. The ground has give, the foundation itself bends a bit. So SSI analysis means accounting for this vertical, horizontal, and rotational flexibility at the foundation level.
And you model this with springs? Did I hear that right?
That's a very common way, yes. We represent the soil's resistance using conceptual springs.
Mm.
Vertical springs for up and down stiffness, horizontal for side to side, and rotational for tilting resistance.
But soil isn't exactly a spring from the hardware store. How do you know how stiff to make these imaginary springs? Soil seems so variable.
It absolutely is variable. And because of that uncertainty, the code, ASCE 7, actually requires engineers to check a range. Usually you calculate a best estimate for the spring stiffness, then you also check the design with stiffness values 50% higher and 50% lower.
Ah, the upper and lower bound approach to cover the bases.
Exactly. And there are established methods to calculate these stiffnesses, referenced in the guide formulas from ACE 41, NIST, people like Gazetas. They depend on the foundation shape length L, with B, and soil properties like shear modulus G and Poisson's ratio.
And does embedment affect these spring stiffnesses too?
Yes, the embedment generally increases the stiffness compared to a foundation just sitting on the surface. The calculation methods account for that as well.
It's getting complicated.
It is. Another way to think about horizontal resistance, especially for embedded foundations, is passive pressure, the soil pushing back on the foundation walls and base friction. ACE 41 even provides ways to estimate how much of that passive pressure you can rely on, depending on how much the foundation moves sideways.
Okay, so adding all this flexibility, that changes the building's natural vibration period, right? You mentioned period lengthening.
Precisely. The flexible base period, which we call T tilde, is longer than the fixed base period, T.
And a longer period means?
It means the building responds differently to the earthquake shaking. Depending on where T falls on the site's response spectrum curve, the forces and displacements could go up or down compared to the fixed base assumption. It's not automatically better or worse.
It just changes things. Does the code account for potential benefits here?
Yes, ASCE 716 has a base shear reduction factor, alpha, meant to capture these SSI effects.
Mm.
But the FEMA guide points out a limitation.
Mm-hmm.
That this factor kind of lumps together the effect of period lengthening and foundation damping, which we'll get to next. It doesn't separate them clearly.
And there are still minimum force requirements, right? You can't reduce the design forces below a certain safety level.
Absolutely. The code has floors on the minimum base shear, so SSI benefits can be capped.
Okay, so let's talk damping. Foundation damping. Sounds like the soil absorbing energy.
That's exactly it. Two main types. Hysteretic damping, which is energy lost within the soil as it deforms, like internal friction.
Okay.
And radiation damping, which is energy radiated away from the foundation by seismic waves traveling out into the surrounding soil mass, like ripples in a pond carrying energy away.
So the soil acts like a shock absorber and lets energy escape. Can engineers always count on this?
Not always. The codes have rules. For example, damping is more readily permitted if the footings are interconnected. For isolated footings, it might not be allowed or it might be reduced. And the simple code methods are really meant for shallow foundations. Deep foundations, like piles, usually need more advanced analysis for damping.
How do they even calculate damping? Sounds even harder than stiffness.
It involves finding an effective damping ratio,
Oh.
0 beta naught. The calculation uses things like a dimensionless frequency AA0, which relates the building period to the soil's wave speed, and other factors based on geometry and soil properties. It gets pretty involved, especially considering those upper and lower bound soil properties again.
Wow, okay. One more modeling challenge the guide mentioned. Basements. Seems super common. How do they handle those with SSI?
Yeah, it's very common, but ASCE 716 is surprisingly light on specific guidance. So engineers use different approaches. Some might just fix the building model at the basement level, ignoring deeper interaction.
Seems too simple, maybe.
It can be, depending. Others build more complex models, including the basement structure and using springs to represent the soil around it.
I think I saw something called a bathtub model.
Yeah, that's one concept. It treats the basement walls as rigid and connects them to the surrounding soil with horizontal springs, like the basement is sitting in a bathtub of soil springs. The guide suggests maybe a simplified version of that, or models where the base is at the bottom of the basement with springs are often reasonable. It depends a bit on whether the building above is mostly frames or walls.
And what about buildings on slopes? That must add another layer of complexity.
Oh, definitely. Unbalanced soil pressures become a significant issue there.
Man, this is a lot to juggle. The guide had design examples, right? Did they help show how this all fits together?
They did, yeah. Very helpful. There's a 2-story steel building example. It shows the whole iterative process. Calculate springs, check damping, see how the ASCE 7 limits on base shear reduction bite, compare results with and without base slab averaging, even though averaging isn't strictly allowed with the simpler analysis they used.
So it shows the real-world trade-offs and code constraints.
Exactly. And it shows how using those upper and lower bound soil stiffnesses affects the design. Then there's a taller 12-story concrete building on deep piles.
Okay, different challenges there.
For sure. This example highlights that the simple damping rules in the code really don't apply well to piles. It points towards using specialized software, like LPile, to analyze the pile behavior, considering group effects, passive pressure on the pile caps. It really demonstrates the interplay between period lengthening and those base shear limits again.
So the examples really ground the theory in practice, showing the complexities engineers face.
Definitely. And the guide concludes by saying, look, SSI is implementable, but it often takes iteration. Generally, it reduces force demands, but can increase displacements.
And the codes sometimes limit how much benefit you can actually take.
Right. Several provisions can cap the reductions. Interestingly, the older performance-based code, ASCE 41, is sometimes less restrictive than the main ASCE 7 code.
And they had suggestions for the code writers, too.
Yeah, things like clarifying definitions, maybe reordering equations for clarity, revisiting the limits on base slab averaging, and calling for more research on things like those upper-lower bound soil properties and seismic pressures on basement walls. The field keeps moving.
Okay, let's try to wrap this up for everyone listening. What's the big takeaway from all this soil structure interaction stuff?
I think the main thing is realizing the ground isn't static. It's an active partner in how a building experiences an earthquake. The building's size, its foundation depth, the soil stiffness, they all matter hugely. SSI analysis is how engineers account for this complex dance to design safer, more resilient buildings.
And those aha moments, for me, it was definitely that flexibility. Even rocking can sometimes be good. And just the scale of a building, changing how it feels, the tremors, it's not intuitive stuff.
Absolutely. It shows the level of sophistication that goes into modern engineering in seismic areas.
Yeah.
You really have to look at the whole system, building and ground together.
So a final thought for you to chew on. We know soil is variable, earthquakes are unpredictable. How might future research, maybe better sensors or computing power, change how we handle SSI? Could we get even smarter, more tailored designs down the line?
That's a great question to end on. I think absolutely. As we get better at characterizing soils, modeling complex behaviors, maybe even using real-time data, we can see designs that are much more finely tuned to their specific site conditions, perhaps even adaptive systems someday. It's a field with a lot of potential for innovation, definitely leading towards safer structures.
Fascinating stuff. Thanks for guiding us through this underground world. That was the deep dive. Join us next time as we keep exploring.